मेरे ऊपर कैमरा दे दो. Good morning, Nick.
Hi, good morning.
Yeah.
Hi, Marcus.
Hello, hi, Nick.
Hello, Marcus.
Hello.
Amit, could you make me a co-host so that I could?
Yes, I will.
Thank you.
We are using so many of batteries every single day. Now the camera cannot be adjusted because the remote control doesn't have batteries.
Okay. Yeah.
So Nick, you have sent the registration link to your students who will be joining us TAs?
Yes, I did. Yeah.
Okay.
I think they were also following it via, well, yesterday via the streaming.
Okay. We spoke to the participants later on, and yeah, all of them enjoyed both your lectures.
Nice to hear. Yeah, this is one thing doesn't work so well on Zoom, right? I mean, them approaching you, asking some questions in person because students want to be too shy to speak up with the whole room.
Right. No, but they got motivated by that. That is more important.
Yes. Now I sent you my slides, but now this morning when I was going over it, I found a lot of typos and repetitions. So
okay.
Once I'm done, I'll send you a new version.
Sure.
But also please tell the students that they're welcome to email us if they have any questions anytime.
Yeah. Sure.
Same here. Should just send an email. Don't be shy. I mean,
yeah.
The only thing is that they get a late reply, or there's no problem.
Yeah. I will let you. Yeah. Purvita is here.
Also for reference requests or something, right? They want to know where to read something. And,
Oh, yeah. Directly? Oh, yeah. I can understand. Oh, hi. Good evening.
Hi, Purvita.
Yeah. So it's for you, it's a good morning, I guess.
Yes.
Yeah. So I think, in 1 minute, maybe we can start.
Already, okay.
During the tutorial, you are going to take help from your two students and...
Yes, they will join and we'll see. I mean, I have a tutorial sheet, but I'm also happy to turn it into a Q&A if they have any questions. So
I see.
They could ask any questions about the lectures as well.
Yeah, that makes sense. Yeah. It's also early morning at Marcus' place, or it's...
Sorry?
It's also early morning at your place, or?
It's okay. It's morning. Yeah, it's morning.
Even earlier, right? 1 hour earlier.
1 hour. It's 10 o'clock here. Yeah.
Today we have fewer online participants.
Yeah.
After dinner was a big party.
Maybe that's it.
That maybe explains it.
Yeah. It's 1 minute left. Just.
Peter,
Did you take any pictures? Because I was also quite curious about the food, at least visually.
No food picture, because when we are taking the food, we were so hungry, we just finished it. And then we took a photography, and that is already there in the website, like at the hall. So sorry for that. Yeah, sometimes you need to come and enjoy the Indian food. It's really good.
Yes, absolutely.
I think Marcus already had the like idea of the food of India, or you came here, no, sometime?
me? Are you asking me?
Yeah, Marcus.
No, I've never been to India.
Oh, never been. Okay,
No,
actually,
no,
Amit told that twice you it was where then? Like you accepted the invitation that he mentioned at some point.
Well, I mean, in the UK, you get reasonably good Indian food, I think.
Oh, that
Well,
is true.
I've never been there, don't know, can't really compare it. But
And that's true. That's true.
it's
Yeah.
definitely better than other countries have eaten Indian food.
Oh, both of you never been in India?
No, not yet,
Oh.
unfortunately.
Next time.
Yeah,
I hope that next time you will be here. That will be
absolutely.
great.
Yes.
Okay, I think that's all the time. So, okay, welcome everyone to the second half of our fifth day of that ISLA. And today, Professor Bezhanishvili is going to continue with his talk from yesterday. So the platform is all yours, Nick. Please take the charge.
Okay, thank you, Purvita. Yeah, so let's start with a quick recap of yesterday, and then so my plan is today to talk about hating algebras and a Sakya duality for hating algebras. But let's recall that this is what we did yesterday. So I discussed in detail the duality between distributive lattices. Again, everywhere assumes that they're bounded, so we have the top and the top and bottom elements. And Marcus talked about the duality for spectral spaces. In particular, this gives us that Priestley spaces and spectral spaces are equivalent, but in fact, even more is true, they are isomorphic. These two categories are isomorphic. And now this is also something Marcus mentioned yesterday. And now let me just briefly recall how on objects, how does that work? So if we have a Priestley space, how do we get the corresponding spectral space? For this, we'll just take what's the topology of open upsets. So we'll take those upsets which are open with respect to this Priestley topology. And this way you get a spectral space, which is isomorphic to the same distributive lattice as this Priestley space. And in particular, the following is true, that then Kloppen upsets of this Priestley space is the same set as, I think Marcus used different notation. I'm just using C or no for compact open. I think Marcus used K. It doesn't matter. So these are compact open sets of X. So compact open sets of X with respect to the spectral topology is the same as Kloppen opens with respect to the Priestley topology. Okay, and this will be, and this is isomorphic to its dual distributive lattice. Now, the other way around, if we start with a spectral space, this is something I also mentioned in my talk, how to get to Priestley spaces. We take the corresponding Priestley space is the following. You take the patch topology, so you take compact opens and their complements, and you declare this as a base and generate topology with it. And you take a specialization order of this spectral space. This is also something that Marcus and also Purvita mentioned in their classes. So a patch topology with specialization order, the specialization order gives us the Priestley space. And again, the same is true. Kloppen upsets with respect of this Priestley space is the same set as compact opens of the spectral space that you start with. And so this equivalence is 1-to-1. And in fact, you start with a spectral space, you go to Priestley space, and when you come back not to an isomorphic one, but even more, you come back to the same one. So it's the identity, you come back to the same X. because we are not changing the underlying set. Okay, one other thing to mention, but I won't say much about it. So given a Priestley space, you also have naturally you can go to spectral space, but you could also go to a bitopological space. So what's a bitopological space? It's a topological space. It's a space with two topologies, tau 1 and tau 2. What are these two topologies? You take open upsets, or you could also take open downsets. And this way you get a bitopological space. And you can develop this way a bitopological duality for distributive lattices and Hating algebras. And here, let me just refer to you to a paper of me and my co-authors. But also, I don't know, I think I mentioned this as one of the topics for student presentations. So I don't know whether anyone will pick up on that. Okay, so I don't want to say much more on this here, but there is, so there's this kind of three worlds, if you like: Priestley, spectral, and bitopological. So we call it pairwise stone. Let me not concentrate on this now. So what I want to talk today about, this is Hating algebras and their duality. Okay, so first, what's a Hating algebra? So it's a bounded lattice. You could also assume that it's distributive, because you don't need to assume, because every Hating algebra you can prove that it's distributive. So it's but it's good to know that Hating algebras, every Hating algebra is based on a distributive lattice. So equipped with a binary operation implication, which is a right adjoint to meet. So in other terms, that for every A, B, and X, we have A meet X is smaller than B, if and only if X is smaller than A implies B. So this is, you can think of it as a binary operation. Let me, before moving to some main properties of Hating algebras, let's at least see, I think Hating algebras pop up in many different areas of mathematics. One of the key connections, this is, unfortunately, I was considering, but most likely I will not have time to talk about this. So in logic, the Hating algebras are algebraic models of intuitionistic logic. This is the same way Boolean algebras correspond to classical logic, and this we've seen at one of the classes in the school. Hating algebras correspond to intuitionistic logic. And they provide the algebraic semantics for intuitionistic logic. In topology, this we'll see, at least as an example, we'll see, but that opens of any topological space form a Hating algebra, and this also, well, developed also using duality into a new area, which is called the point-free topology. So instead of doing topology sets, set-based topology or point set topology, you could work with Hating algebra with open sets and develop topology using this Hating algebra. And this is called, this area, relatively new area, a few decades old area, is called the point-free topology. Recent applications on geometry also, that if you take some polyhedra, a geometric object, and open subpolyhedra of a polyhedra, form a Hating algebra, which also points to interesting connections to geometry. In category series, this is a classic fact that the Sauer classifier of any topos is a Hating algebra. And this led also to a lot of connections with categorical logic. Universal algebra, so lattices of all congruences of any lattice also forms a Hating algebra. And these are only a few, there are even more connections, but let me not go into this now. For us, of course, the main one for interest is connection with logic and also connection with topology. Now, for Hating algebras, if you look at the definition, this is not an equational definition. We say that this is an operation satisfying this. I mean, this is not an equation. Now, in logic in general, or in universal algebra, it's also important, if you can, to have an equational definition, because equationally definable classes, they're good classes by Birkhoff theorem. These are varieties. And so it's also good to have an equational definition. And so here's a different definition of hating algebras, which is equational. Oh, sorry, that this number, it shouldn't be there. So a bounded lattice is a hating algebra if and only if there's a binary operation satisfying the following 4 equations. Again, they had many different equivalent equational characterizations of hating algebras, and this is one of them. So if these 4 equations hold, then this algebra is a hating algebra. Okay, let's see. I have quite a few results with proofs here, and some of the proofs I would like to skip, but they will be on the slides, so you will be able to see. I don't know. Do we want to see this? Maybe this is one of the proofs that I would like to skip, right? So this is, but you could consult. So one direction is a relatively easy exercise, and the proof of the other one, how these equations guarantees that we have a hating algebra, that this implication is an adjoint of meat. I think it's on the slide, but let me skip it. Okay, next fact. So if we have a complete lattice, then A is a hating algebra if and only if it satisfies. So not every complete lattice is a hating algebra, but it's a hating algebra if it satisfies the so-called infinite distributivity law. And also note that there are usually 2 infinite distributivity laws. One that meat commutes with infinite joins, and then another one, join commutes with infinite meat. So in fact, here we state one, the other one will not be true, but this is in a hating algebra, this is always satisfied. Probably this is yet another proof that I would want to skip for now. Here's maybe one aspect. Yeah, no, let me maybe skip this proof. So one thing to remember, that if we have an infinite distributive lattice, how do we show that it's a hating algebra? We just say this: take A implies B and let it be. This will also show up very soon. So A implies B is the join of all those C's that C meet A is smaller than B. Well, why do we know that it exists? It exists because the lattice is complete, right? So this is an infinite join. So it's in supremum of the set. And so if an algebra satisfies infinite distributivity law, and it's complete, we just take A implies B, we define it like this, and then we need to show that it is, in fact, makes it a hating implication. Okay, well, let's look at some examples now. I claim that every finite distributive lattice is a hating algebra. Maybe just to make sure that students are with me. So why is this true? Why is this a corollary?
Any answer from the student?
So the corollary 2 just follows from the theorem which you proved here. The
Yes.
corollary 2.
Yes, indeed. And why?
So because it follows infinite distributivity, so that's why.
Yes, because if you take a finite distributive lattice, it's complete. So for finite posets, being a lattice and being a complete lattice, it's the same thing. It's finite. So every finite one is a lattice, and then infinite distributivity in the finite case becomes just standard distributivity, right? So complete finite lattice satisfying infinite distributivity law is just a finite distributive lattice. And indeed, so then we get that every finite lattice is a hating algebra. Another one, this is exactly the reason why I didn't want to put distributivity in the definition, because you could get it. Now, this follows maybe not so much exactly from the theorem, but from its proof. If you analyze the proof, you could easily see The same way you prove that if A is a Hating algebra, it satisfies infinite distributivity law. The same way you prove that it satisfies the distributivity law. So it follows that this fact follows from this proof. And in fact, that's the reason that we don't put distributivity in the definition of Hating algebras, because we can derive. Okay, this is I guess what we said. Another interesting fact, right? So if A is a Hating algebra, then the implication, this is how you can prove it, that this is what the implication is. Now, there's one subtle thing. It could be that this join exists, but the algebra is still not a Hating algebra. Why? Because let's take a complete lattice. In complete lattice, every join exists. So in particular, this join will exist. But this theorem exactly tells us that this is not enough to be complete, right? We also need the infinite distributivity law to be satisfied. Okay, so, but if A is a Hating algebra, then this implication is, this is how we compute the implication. Now, few other examples of Hating algebras. And so this I leave as easy exercises. Every Boolean algebra is in fact a Hating algebra, where the implication is, as you expect, is A implies B is not A or B. Another one, every linear lattice, so every chain which is bounded with top and bottom elements is also a Hating algebra. And there you could see that, you know, if you look how A implies B would be, maybe we could quickly draw this. So if, yeah. So think of any chain, right? So this is top element, this is bottom. So we look at A and B. So let's see first, let's see A and B. So suppose A implies B, what should this be? So we look at this set of all C's such that C meet A is smaller than B. Because A is small, C, because what am I saying? Yeah, because A is smaller than B, any C will be less than B. So for any C, C meet A will always be smaller than B. Okay, so any C satisfies. So basically, this set is in this case is A, and so its meet is 1. So A implies B should be 1 if we take this as a definition. Now, if it's the other way around, if this is A and this is B, let's look at what is the set of those C such that, so basically, if this is my A, I should erase it better. No. Okay, so this is my A. Yes, thanks. This is my B. We look at this set, all those C's. So the C meet A is smaller than B. So then it will be just this set, all those. And indeed, so it's all those C's such that C meet, because this is, wait a second. Yeah, C meet A should be smaller than B. So it will be just this guys. And then their join will be B. So this is the way to memorize or to compute. So in the linear ones, this is how you compute the implication. A implies B is either 1 or B. Yeah, we could, with this definition, we could check that with this definition, then it's this is really a hating algebra. So this also leave as an exercise that A implies B defined this way will exactly be the adjoint of need. But keep in mind that this need not be any chain, complete or not, forms a hating algebra with this definition. So now we have a lot of new examples.
So this is the Gödel arrow, right? That A arrow B equals to 1 if A less equals to B.
This is Gödel arrow, yeah. Linear. So I call them linear hating algebras, but in fact, in other standard definition, is a Gödel hating algebra, right? Yeah. So this different. It comes more from MV algebras or fuzzy logics, the name Gödel algebras. Linear ones more from the theory of hating algebras, but this is the same thing. You're absolutely right. Okay, we'll see more examples of hating algebras in this course. Yeah, so here it is, the connection with the topology. So let's take a topological space and let tau be the open sets of the topology. Then this is a distributive lattice. Probably you've seen that well, or at least easy to see. So the open sets are closed under finite unions and intersections. Moreover, I claim that it is a complete distributive lattice. Now, in order to check that something is complete, it's enough to check that all the suprema exist, because infima is also a supremum of that. It's what infima is supremum of all the lower bounds. So it's complete because if you take every subset, supremum of S or join of S is the union of S, and union of open sets is open. This also means that that infima also, as I said, infima also exists. But note, okay, I was too quick. Usually, this is something that I ask students, so I this wasn't supposed. I should have hidden this final line, right? Okay, well, this spoils it a bit, but let's see. The infimum will not be the intersection. So the supremum is the intersection, but the infimum is not an intersection. Because, well, the intersection of open sets, think of the real line, takes open intervals, say, which are converging to 0. These are all the open set, and the intersection is just 0.0, right, which is not open. But we know that it exists. So what's the trick? Well, the trick is that, it exists, but no one says that it must be the intersection. It will be, in fact, in this case, the interior of the intersection, the greatest open set inside this intersection. So this will be interior of that. Okay, so this is an example of a lattice which is complete. Suprema are unions, but infima are interior of intersections. The infinite one. In the finite case, you can get rid of it because in the finite case, it will be just intersection. Okay, now the question is, so this is a complete lattice. Is it a hating algebra? Well, it is a hating algebra because we need to check that the infinite distributivity law is satisfied. But let's see, well, meet is intersection, join is a union. So we just get, well, this is what we need to check. This is what the infinite distributivity law boils down. But this is clearly true because we are working with sets, right? So it easily say if X belongs to this part, it belongs to the other side. So every opens of every topological space form a hating algebra. And this is a good example of a hating algebra where the other infinite distributivity law is not satisfied. Why? Because here, this is a finite union, but this is, as we said, it's not an intersection. It's the interior of the intersection. This is also interior. It's a good exercise to check that why it is not satisfied. I mean, I don't have personally now an example on the top of my head. So it needs a bit of thinking, but this is definitely not true in general. So think why not, and think what would be a good counterexample to that. Okay, well, because it's a hating algebra, we know that U implies V exists, and it must be the join of all those C's such that C is in tau, so it's an open set, and C meet U is smaller than V. This is easily shown that this is the same. I guess you take, what do you take? You take the union with not U on both sides. So it's easily seen that this is the same set as that. So those C's in tau such that C is subset of not U or V. I'm saying no complement of U or V.
Hello, sir. Yeah,
Yes.
The meet is the interior of the intersections, or meet is just intersections?
You mean here?
Huh?
Yes.
This meet?
This meets?
Yeah, because, well, here, yeah, well, this is a meet is the intersection, because if you take two open sets, their intersection is open, or intersection of open sets is open. Infinite intersection of open sets may not be open, but finite intersection is always open. So this forms a distributive lattice. Yeah, you need to check, but basically it's easy to see that intersection and union will be meets and joins here. So finite meets and finite intersection are finite meets and finite joins are meets and finite meets and finite intersection. But the infinite one is not in general. So you need to add interior. Okay. And yeah, so here, this would be finite union, but this is interior of the intersection. Now here, this is equivalent to this. So this set is easily seen to be the same as this set. But note again, this is again a spoiler. So usually I ask, what is this set? So we look at all the open sets in all the C's in tau, so all the open sets which are inside some set. So this you should remember from Purbita's class that this is just nothing but interior of this set. Okay. So hating implication is, so think of this. This is a classical implication, not U or V. Right? So this is how you compute it in a Boolean algebra, in the power set algebra. And then how do you compute the hating implication? This is interior of not U or V. So classical implication and interior applied to. Okay, this also suggests some connections between model logic and intuitionistic logic. This is for whoever is familiar with Gödel embedding of intuitionistic logic into classical logic. This is kind of an topological interpretation of that implication, that box or like interior of a classical implication, it's an intuitionistic implication. If you are not familiar with that, then this will not play a role for us. Okay, well, with this, now I can, yes, I can already refute the so-called the law of excluded middle in topological spaces. So let's take the following example. Let's take the real line. And I claim, let's take this interval U, 0, infinity. Let this be U. Maybe a question to the audience. Yeah, let's also think what would be negation of U of A in general. Yeah, maybe this I didn't put on the slide. This is, as you probably know, A implies 0. So this is how we define the negation. Now let's see what should be not U. Not U should be what? Interior. So U implies 0. So V disappears. So this would be the interior of the complement of U. U complement. Okay, so question to the audience. So what will be, can you compute the set? So what U join, so that will be U union, not U. If U is 0, infinity.
It will be R minus 0.
R minus 0, indeed. So if you take U is this set, its complement would be something with 0, but then interior will get rid of 0. So it will be R minus 0. Indeed, everything but this point. Well, you could see that this is not 1. This is not R, because this would be R minus 0. Now let me write 0, although it should be singleton 0, right? But this is not equal to 1, because 1 is R in my case. Everything. So we see we just refuted this law, this classic law of the law of classical logic is not true on this, for example, Hating algebra of open sets. So we again see more examples of, so every Boolean algebra is Hating algebra. Every linear chain is a Hating algebra. Every complete distributive lattice with satisfying infinite distributivity law is a Hating algebra. In particular, every topology of every topological space is a Hating algebra. Okay. Now I want to concentrate even on a subcase of this. So given a poset, again, we remember what an upset is, right? So this we worked with a lot last time. Now we also have a notion of a downset. So complements of upsets are downsets. Now note that the upsets and downsets are closed under arbitrary intersection. So for example, up P is closed under arbitrary unions and intersections. So I don't know, Purbita, did you mention Alexander topology in your tutorial?
Not in my tutorial, but at some point I think someone did. I forget.
Yeah. Okay. Okay. Good. So if this gives us up P, gives me a topology on a P, which is called the Alexander topology. So this is a special topology because not only here open sets up P is not only closed under arbitrary unions, but it's also closed under arbitrary intersections. And so if up P are open sets, then closed sets will be their complement, so they will be down sets. And moreover, in this topology, though, if you have not seen it, it's also a good exercise. Interior of a set, this is set of these points such that up arrow X is a subset of U, and closure of a set, this is even easier. So this is a downset of everything below it. This will be the closure of my set. So this is closure and this is interior. In particular, so let's see. This is, so poset with Alexander topology is an example of a topological space. So it is a Hating algebra. So U implies V should be computed, as we said, it's interior of the complement U of U union V. Now, there is a special connection between interior and closure. So interior is not closure not. So if you see, I'll come back to it at the next line. So it's a, what is it? So yeah, this set complement closure not. Complement closure complement. So in other terms, now let's spell out closure is the downset. So it is this set. I think one of the complement is missing. Complement downset complement. So now let's look at this set and let's do the De Morgan law inside here. Probably I already did De Morgan's, that's why I get rid of it. So if you do De Morgan's there, you get this set. And basically this is U minus V. U intersects is complement of V, it's U minus V. So what did we get? That U implies V is U minus V, downset and complement. In other terms, this is just set of those points if you spell out. This is those X, such that up arrow X is a subset of the complement. So up arrow means everything above X. Is either in complement of U or is in V. Now, why did I put this last thing? So this is exactly those for you who are familiar with the interpretation Kripke semantics of intuitionistic logic, this is exactly how you interpret implication in the Kripke semantics. Basically, you say that X satisfies phi implies psi in intuitionistic logic if in any successor of X, either phi is false or psi is true. Right? So this is exactly the intuitionistic semantics of implication. Again, we will not be talking too much about logic here, but this is also something to remember. So if you interpret U implies V in this Alexandrov space, you just get exactly interpretation of intuitionistic logic. Okay, we'll come back. This will play a session role for us, right? So we'll definitely come back to it. Are there any questions so far? You could also ask them afterwards, or it's a tutorial. So, yeah.
I was telling that not from the offline participants, at least.
Okay. Now let's move. I mean, this will play a role for us, so let's not forget it. But now let's move to Esakya duality, and this was also developed by Esakya, independently from Priestley, and I'll also mention that in a moment. So we want now to have the same. Yeah, one thing we could, from the point of a Priestley duality, we could think like that. So these are distributive lattices. And we can think of Esakya space, Hating algebras, those distributive lattices where you can define implication. These are not all of them, but some of them. So you could think of this as Hating algebras as kind of subclass. From the point of view of a lattice, Hating lattices will be a subclass of distributive lattices. Okay, on the other hand, here we have, this is what we already seen. We have Priestley spaces. These are duals to distributive lattice. And then the question could be, which Priestley spaces correspond to Esakya spaces? How to characterize among the Priestley spaces, how to characterize those which satisfies the extra condition, which correspond to Hating algebras. And this is what Esakya did. But he was thinking a bit differently, and I'll also mention Esakya's original definition. But this is our goal. So we have a duality for distributive lattices, and now we want a duality for Hating lattices, Hating algebras, and then how to restrict Priestley duality to get what we'll call the Esakya duality. So suppose we have a Priestley space. And again, let's see. So if we have U and V in Clopens, we know that, okay, this is probably in fact what I did in the previous slide. So U implies V, as we said, it's interior of, and now instead of writing U complement, so instead of X minus U, I'll just write not U, just because to simplify the notation. So this is the complement, and this is downset, as I said. And basically, once again, so U implies V is interior of the class. This is classic implication, and this is interior of the classic implication. So interior and closure is downset, interior is not, closure not. So again, this is what we already had. Not, closure not, use the De Morgan law, and basically this is what we get. That implication U implies V is in posets U minus V downset at its complement. Now, if we want to think our distributive lattice from the duality perspective is Klopen upsets, okay, of a Priestley space X. And if we think that this is how we should define the Hating implication, basically what we need to demand is that if U and V are Klopen upsets, then this operation is also a Klopen upset. Well, it's a Klopen upset means that its complement, so just this, should be a Klopen downset, right? The complement of an upset is an upset, and complement of Klopen is also Klopen. So, but note that this set is always a downset, because I'm taking everything underneath. So basically, all we need to demand is somehow that U minus V and its downset This is just Klopen. So this is well defined on Klopens if and only if this is a Klopen for U and V Klopen upsets. And basically this set, Klopen upset minus another Klopen upset, it's easily seen, well, it's a Klopen, and in fact, every Klopen is to some extent of this shape, or at least a finite union of this. So basically this condition boils down to the fact that for every Klopen W, I want its downset to be Klopen set. So this is what leads to our intuitive explanation for the following definition. So an Esakya space is the Priestley space where for every Klopen set U, its downset is also a Klopen set. So this is the definition of an Esakya space. I want to now spend some time on giving some intuition and going through some examples. But before doing that, I want to mention Esakya was thinking a bit differently, and his definition was a bit different. Let's see. His definition was that Esakya space is a stone space, okay, where this is a poset, okay, this is all true in Priestley spaces. But instead of the Priestley condition, he had the following, that upset of X is closed for every X. And then this condition of, so basically the only difference between Esakya's definition and ours was different. We are here taking that, we are saying that let this be the Priestley separation axiom, where Esakya had it, and in fact this condition might be even easier. Up arrow of every this is more common if you look at duality from modologic perspective, that up arrow of every X is a closed set. Okay, so these two definitions are equivalent. This is a good exercise to check. And in fact, well, we'll have it as a tutorial. It's also easy to check that this is true on every Priestley space. So if you have a Priestley space, then it is also called point closedness. For every point, everything above it is closed. But the other way around in general, so this condition is weaker than weaker or stronger. Basically, this condition may not imply, I guess weaker, may not imply Priestley separation. And here's, let's maybe look at this example, easy example. So let's again work with our standard counterexample, finite, cofinite with the, so Alexandrov compactification of natural numbers. So topology is finite, cofinite. So here I have 0, 1, and so on. 2, and so on. And we also have the compactification point omega, and let's put it on top of it. So here's omega is above everything. So this is my space. Now I claim that this is point closed. Indeed, if you take any point X, then the set of points above it is a finite set. Right, so it's a finite set, and so every point is closed. So every finite set is closed in any stone space. So is that clear? So this would be a point closed space, but this does not satisfy the Priestley separation axiom. Why does it not satisfy the Priestley separation axiom? Because, for example, omega does not see point 0, but every Klopen upset or every upset that contains, omega doesn't, it's not smaller than 0. But now every Klopen set that contains omega should contain, it must be cofinite. So it must contain cofinitely many points from here. But every cofinite set here is in fact everything, because every cofinite upset is everything. I mean, to satisfy Priestley separation axiom, this separating set should not only be Klopen, but it must also be an upset. I claim that there's no upset that separates omega from any other. There's no Klopen upset that separates omega from any other set, right? Because this upset must be Klopen, it must contain cofinitely many sets, so it must be everything. So it cannot separate omega from 0. Is that clear? or if not, think yourself. So in fact, 3 is different from Priestley separation axiom, but together with 4, it's equivalent, and it's a good exercise to see why is that the case. So point closedness and this condition implies the Priestley separation axiom. Okay, so take the definition you like, this one, or we have a Priestley space with this condition. Now let's look at a few examples. So let's look at our classic example, or there's 2 examples of Priestley, again, with on finite, cofinite, and let's put omega on top. Now question, top means this is related, these are all connected. So question to the audience, is this the Sakya space? Does it satisfy? It's a Priestley space, this we already checked. Does it satisfy the extra condition?
Yes, here.
Okay, and let me also immediately to make it, let's look at its dual version, right? So let's put omega at the bottom. And then a follow-up question, or is this an Sakya space? Yeah, Prabita, someone had an answer already?
Yeah. Like you want to say something, you can just.
No, I don't think it's dual. That's
So is X1 the Sakya space?
yeah, I think so.
Yes. Why? If we take any Kloppen set, so it should be finite here, its downset will be itself, right? So we're fine. And if we take a cofinite one, it must contain omega, right? If it contains omega, its downset is everything. So it's again Kloppen. Is that what you had in mind?
Yes, sir.
Yes, good. How about X2? Is X2 a Sakya space?
No, I don't think so.
Why not?
So it's just a singleton point if we will take the downside.
Yeah, let's take some singletons, they say. It's a Kloppen, its downset would be, say, if this is 0, its downset would be 0 omega. This is not Kloppen because it's neither finite within N and neither cofinite containing omega. So indeed, so this is not an Sakya space, although it was Priestley, and this is. Now, I let you check that if you do it the standard order, if you put the compactification point now here, this is, so again, if you take any Kloppen containing omega, its downset is everything. So you could immediately see that this is in a Sakya space that, or Priestley space, which in a Sakya space. And so is this. If you take any Kloppen, then its downset is again Kloppen. So we are fine again. So this is a Sakya space, this too, but not that. So no, clearly not every Priestley space in Sakya space. By the way, talking about, so what do you think, so Kloppen upset, distributive lattice of Kloppen upsets here. What would you get via Kloppen upsets? Or at least, yeah, let me say so. So what we get all the cofinite sets with omega. So roughly speaking, you can think of it, if you take, this is isomorphic to, even if you take N, and if you look at all the cofinite sets with 0, with the empty set. So this is cofinite. So this is the distributive lattice that you will get. And in fact, you could also show this isomorphic to this distributive lattice. And you could show that this is also a Heyting algebra. If you look at Kloppen upsets here, this is isomorphic to a distributive lattice of finite ones. So finite and everything. This one element on top. And this you could show that this one is not a Heyting algebra. Although both are distributive lattices, but not a Heyting algebra. Okay, so I hope you'll get some. By the way, yeah. Also, Marcus mentioned in his talks that indeed spectral spaces are topological spaces without order, and that makes them kind of attractive, especially for people who are used to thinking in terms of topologies. And these are order Esaki space and Priestley spaces are indeed ordered topological spaces, or they are not topological spaces as such. So one could say this is, but this is a feature, right? So it's also a disadvantage maybe, but its advantage is that you could also draw pictures much easier with that, because the order allows me to draw pictures. So I immediately draw some pictures, and most of the proofs that we've given so far were proofs by picture, right? So that's also the advantage, so to say, that yeah, it also gives extra spatial intuition, and I'll try to illustrate that later in today's lecture. Okay, let's move on. So this was our alternative, and now I want to quickly sketch the Sakya duality, and again, probably I'll try to skip most of the proofs. So, like in the Priestley case, we have, if we start with an Sakya space, then I claim that the functor is the same. We take Kloppen upsets, but now our operations are not only lattice operations, but we also have the implication, and I claim that the implication is of this kind. So that this is A implies U implies V is, as we said, complement of U minus V downset complement. Yeah, maybe it looks a bit complicated, but if you get used to it, it's not so bad. And I guess this is an exercise to show that this is indeed a Hating algebra, that this implication makes it a Hating algebra. Moreover, I claim the following is true, that if we start with a Hating algebra, we look at the Priestley space, and we have this embedding. So we have A, and we know that we have this map, which again I call phi, Marcus called it V, into Kloppen upsets. Now we know that Kloppen upsets, I can think of them as also as a Hating algebra, because I know that phi was a surjective, injective, and so basically what was a lattice isomorphism. What I claim now, and what this proposition says, that in fact it's not only a lattice homomorphism, but it's a Hating algebra homomorphism, that it also preserves the implication. This is again not obvious, but it's true. So because of that, if I prove this, I can show that Priestley duality plus this fact gives me that a representation of Hating algebras. I could say that every Hating algebra is, well, at least is isomorphic to Kloppen upsets of its corresponding Priestley space. But then we also see that its corresponding Priestley space for a Hating algebra is an Esaki space. Okay. So I have a proof of this fact on the slides, but maybe let me skip it. So you prove it by her. So if X is in one hand side, we show that it's in here using this interpretation of the implication. Phi A is a set, it's U, phi B is V, and we just say that if X is here, then it's there. So this is one direction. Again, it's easy to follow. So, and the other way around, we prove by contraposition. We say that X is not here, and then we show that X is not there. So, and then we need again to apply the prime filter theorem. Again, we need to work with filters and ideals and find the prime filter which would give us the element Y, which is above X, such that, so will give us that Y, which is above X, and which is such that Y is in here and Y is not there, contradicting to this fact. Okay, so I'll leave the proofs here on the slide, and we'll move on. So another proposition that we need to prove is that if A is a Hating algebra and XA is dual Priestley space, this is what I just said, then it turns out that it's not only a Priestley space, but it is also an Esaki space. And again, I have a proof of this on the slide, but I just want to it's a, as you see, it's a short proof, but so basically we have every Kloppen has a particular representation. And because of this, down set of U can be, I can see the down set of U for any set is a union, finite union of some elements of the shape or complements of the shape phi of some implication. But because of this is Kloppen. In fact, it's Kloppen upset. This is its complement, and there also finite union is a Kloppen set. So down set of any Kloppen is Kloppen. This is what this fact shows. So again, this dual, so prime filters with the Priestley topology is an Esaki space. So what do we have? We start with a Hating algebra. We take its dual, now let's call it dual Esaki space. And we take its Kloppen upsets, and then what we showed, that's the same, that this map phi is a Hating algebra isomorphism. So this is our representation of Hating algebras and also duality for objects. And the same is true. So if you start with an Esaki space, you go to its dual. So again, we have the following, these functors on objects, at least. Well, I'll say something about this soon. Well, let me just at least know. So we have Hating algebras here. We'll see this in a moment. We have Esaki spaces here. And we are going from Hating algebras to Esaki spaces and backwards. And this shows that on morphisms, or on objects, we have the corresponding, we have a dual equivalence. We have equivalence, duality will come with morphism. Okay, and this phi is an isomorphism between A and Kloppen A. So this gives me a representation of Hating algebras. So Esaki representation. Every Hating algebra is isomorphic to the, this is too, I bad copy pasted. Is isomorphic to the Hating algebra Klopp up X for some Esaki space X. And I copied it from the Priestley part. Now I claim in the same ways that for Priestley spaces, we observed that every finite Priestley space was discrete, so Kloppens were everything. The same is true here. Every finite Hating algebra is isomorphic to up X seen as a Hating algebra for some finite poset X. Right? So we have the same. So for finite Hating algebras, again, you can forget any topology. You work only with posets. Now, we still need to talk about morphisms, right? Because if you want to talk about categorical equivalence, you need to mention morphisms. So what are the morphisms? Well, the Esaki morphisms are different than Priestley morphisms because they also take into account, they also need to take into account implication. So what's an Esaki morphism? So an Esaki morphism is a Priestley morphism. So a continuous order preserving map, which in addition satisfies the following condition, which might seem familiar for people again that's in model or intuitionistic logic. So let's see what it says. So if we have X here, X is mapped to f of X. So from f of X, we go up to some point Y. And this says that there exists Z such that fz is exactly mapped to Y. And who is familiar with the notion of bisimulation from modology? This is a functional bisimulation, or in other terminologies, p-morphism or a bounded morphism. Okay, or those who, in terms of posets, so a monotone map in terms of posets, so in terms of Alexandrov spaces, corresponds to continuity And this condition corresponds to openness of that map. And map is open if direct image of an open set is open. So this is in fact equivalent to saying that direct image of an upset is an upset. And monotonicity is equivalent to saying that inverse image of an upset is an upset. Okay. Now, why do we need this condition? Because, yeah, this is what I said, it's related to bounded morphism model logic. Because with this condition, you could show that F inverse or F star, this map now preserves implication. So F minus 1 U implies V, now with this condition, gives me that this equality. Again, this is another good exercise that I'll skip for now, but maybe we could discuss it as a tutorial. It's a straightforward. By applying this condition, it's kind of straightforward to check that basically this equality holds for, you assume that X belongs here and you show that X belongs there and vice versa. Okay, so Esaki morphisms are Priestley morphisms satisfying the additional condition. Now, what does this give? So here I call it an exercise, but in fact, if I know this is straightforward. If we have, again, let's see, this is our duality picture. We have X, we have Y, and we have F. Now we look at Kloppen upsets of Y. We look at Kloppen upsets of X, and the duality tells us that then this map gets reversed. So we got F star, which is going in the other direction. What does it do? F star is exactly F inverse. So it takes Kloppen upset U in Y and takes its pre-image in X. We already seen that it's a distributive lattice morphism, so it preserves meets, intersections, and well, it also preserves complements, but says we don't worry, we don't have complement in our signature. It presents top and bottom, but because of the previous result, if F satisfies the extra condition, it also preserves the implication. So it is a Hating algebra homomorphism. What's a Hating algebra homomorphism? Well, it's a homomorphism that preserves all the structure. In particular, it should preserve the implication as well. So Hating algebra homomorphisms are those lattice homomorphisms. They also preserve the Hating implication. So HA implies B. This should be HA implies HP, right? Homomorphism in algebra is always kind of straightforward. It should preserve all your algebraic structure. Okay. Next, we have the same picture the other way around. So if we have A and B, I can draw that. Well, maybe I don't need to draw it, right? So we have two algebras. Then we have Hating algebra homomorphism here. And then H star now will be, so we know that it's a continuous and monotone. This is by Priestley duality. And H star is defined by just H inverse. Take any element here, which will be a prime filter in B. We take its inverse image, it's a prime filter in A. But moreover, we claim that it's also now an Esaki morphism, so it's in addition satisfies this condition. H star satisfies this condition. Again, I don't have a proof of this, but it's a good exercise. It's not so straightforward. It needs some arguments. maybe I'll put it once I prepare the final version of the slides, probably later today. I may put the proof on the slides because this is a bit trickier than the one for Priestley spaces. But so it's a good exercise. I'll leave it as an exercise for now. But so we have now correspondence between. So here I can now talk about the categories. So we have the category of Esakia spaces and morphes which are continuous. So Esakia morphes. So continuous, monotone, and satisfying the extra condition. And we have AHA, the category of hating algebras and hating algebra homomorphisms. Okay, and now the Esakia duality tells us that we have it's one-to-one correspondence. So we take hating algebras and we take Esakia spaces. Here we have this map, which I call spec. I think Marcus also called it spec. So what's a spectrum of a hating algebra? It's a Esakia space of its prime filters. Now, what is the map backwards? So this is, we are taking Kloppen upsets of an Esakia space. And what does this correspondence tell you? That if we start with a hating algebra A, we take its corresponding Esakia space XA, and we take the corresponding hating algebra, plop up of XA. And this map phi makes sure that we have an isomorphism. So we came the same thing. And the same happens the other way around. And one needs to check that the same is happening. So I discussed how the morphism, how the correspondence works on morphism. One needs to show that this is also one-to-one. Right? That it also this establishes the duality for morphisms as well. With all this in mind, then we have our duality. And the final thing I want to discuss now, just to give at least one application of the duality. So as we know, the duality. So the duality, or maybe, the duality comes, as I mentioned early on, with a duality dictionary, right? So duality dictionary. So every concept on the algebra side, I can translate to the spatial case, and backwards. So again, I'm not discussing all of it, but in particular, for example, homomorphic image algebraically corresponds to closed upset on this case, on the spatial side. So in particular, one way to see it, maybe homomorphic images in hating algebras are in one-to-one correspondence with filters of a hating algebra. And filter corresponds to closed upsets. This is also true for Priestley spaces. So you are taking just intersection of all the phi of A such that A is in F, and this is, you are intersecting Kloppen upsets, and this intersection is in fact closed upset. And it's easy to see that, or at least, well, it can be shown that this is one-to-one correspondence, and moreover, it gives you an isomorphism of a poset of dual isomorphism of poseted filters and closed upsets of an Esakia space. Okay, why this can be useful? So let me give you just one example of that. So let's look at this beautiful structure, which is called the Rieger-Nishimura lattice, which is also an important one from the point of view of theory of hating algebras, because it is one generated free hating algebra. Okay, that's in fact, if we have this generator G, it's easy to see that every element, okay, assuming that we understand this goes on like infinitely, right? So it's a recursive definition. Every element of this is generated by G. This is not what so important for us, but yeah, maybe so G. This would be also a good example to see how the Hating implication works. This is not G, right? The greatest element such that its meet with G is 0, right? Because if for any other element, the meet with G is not 0. Then okay, maybe so what should be, just to see that students are, what should be this element, let's say, in terms of G? I claim every element here is kind of a polynomial of G. Or what should be this element? Okay, well, that's easy. This is G join not G. What should be this element?
That should be the negation of the join.
Negation of the join, the greatest element whose meet with the join is
The one on the left. Yeah, the
This
one on
one.
the left is the negation of the join.
one on the left. So this one, you mean, is a negation of the join. Maybe it's an, but is it a negation of something even simpler?
Double negation.
Double negation, yes. I don't think it would be fully negation, but this would, yeah, this is a join, as I said.
Yeah.
And this is the double negation, indeed, because this is a great element whose, or greatest element whose meet with not G is 0.
But that should also be the negation of G join negation G.
Could be, but how about this element? It's also,
Yeah, the same.
yeah, could be. Yeah, it might be the same. But this is easier, right? So,
Yeah.
then next we take the join of these two, right? So what is this? Yeah, for example, this is not G join not G, but it's also true that it will be join of these two, right? So it's also this not G join not G. It's the same as not G join that, right? But you know, I can get rid of that. I don't know what should be this element. Yeah, this may not be easy to see. Is anyone courageous enough to tell me what will this element be?
Oh yeah. No.
Sir, not G join not G.
Not G join.
Uh,
No, the not G join not G is this one.
No, sir, not and in the bracket G join not G.
G join not G. Well, I mean, this one I cannot see how you do represent it as a join. So that's a. This is not a join. This is not a join.
Again.
So here you need to think in terms of the implication.
Sir, double negation of G join not G.
Double negation of G join not G. I don't see.
Right?
Yeah.
Just show it.
Maybe it's equivalent. But no, I think you need to use implication more. Okay, maybe I should stop torturing you. In fact, I also don't see it immediately. Let's see what. So how about this? Not G implies G. So we say that this is the greatest element whose meet with not G is less than or equal than G, right? Do we agree? So the greatest element whose meet with this is less than or equal than that. Yeah, I don't have, so, but here's two things to remember, like about this structure. Every element can be expressed by the so-called Riga-Nishimura polynomial. I can give you a reference where to find it, or maybe I could put it also, I can try to put it on the slides if you like. There are two kinds of elements. those that are joins, and I'll try of this kind, so joins and implications, right? So we gave, so this will be again in implications. This is a join, that's a join, the other one is implication, and so on. Okay? And this goes recursive. So this, for one thing, this shows something else. So this shows that they exist. This is known as a notion of local finiteness, but this shows that they exist finitely generated infinite Hating algebras. So this Hating algebra is infinite. It's generated by just one element. So every element, so if you take the smallest subalgebra is containing G, it will be everything. So this shows that the Hating algebra is a kind of more complicated variety, so a more complicated class, because in distributive lattices, this cannot happen. If you have finitely many generators, what you generate is always finite, whereas here it's, well, we have an example of it being infinite. But in fact, this is not, well, I also want to illustrate something else with this picture. Let's look, what would be its dual structure now? The Esaki space of its prime filters. Again, it's not so easy. First of all, note, will it have the least element, the Esaki space?
So 0 is the least element.
0 is the least element of my Hating algebra, but now I'm talking about its the Esaki space of its prime filters. Will there be the least prime filter?
But it is G or negation G. Okay, take it.
G or negation G, I think.
So think of this. If I have A, I have it's the Hating algebra of its prime filters, and I'm ordering it with the inclusion. So think of this as prime filters. So which prime filter, but the order is by inclusion. So does there exist the smallest prime filter? Right? Not the, so the ones that you are suggesting, yeah, these are good G and not G, right? They will be prime filters, but they will be in fact maximal.
Mm-hmm.
Right?
The only containing one.
Yes, exactly. This one, right? This will be the least prime filter. Okay? And then this ones, in fact, will have two maximal prime filters, right? The one generated by G and the one generated by not G. And in general, note that this guy will not give me a prime filter, right? Because this is not prime. I can get to it. So if it's something is a join, it's not prime, and whereas these ones will be prime. So these are exactly the prime filters. These edges will give me prime filters, whereas these things inside, they will not be prime. Okay, good. So this gives us enough intuition so that I claim this is exactly our dual space. We have the least element. This is prime filter generated by G. Here, this is when I write G, I mean the prime filter generated by elements. So as you notice, this will give me a prime filter, and that will be prime filter generated by G. This will be prime filter generated by not G. This will be prime filter generated by not G, and so on, right? So exactly this edges will give me. So this is my picture. This is, well, the dual space of dual Esaki space of it. And this one, if the one is called Rieger-Nishimura lattice, the other one is called the Rieger-Nishimura lattice. Okay, now the question. So my goal is kind of to illustrate that this dual picture is kind of very helpful, and often even at least in my view, more informative than the lattice itself. So here's a question. Can you characterize, and now let's forget whether that Rieger-Nishimura lattice is one generated or not, but the question, characterize, suppose we are interested in this, and yeah, I can give you many reasons why we might be interested in that. All homomorphic images of the Rieger-Nishimura lattice. Okay, fair question. Can you do it? all homomorphic images here. Well, I believe, yeah, only thinking algebraically. I believe probably yes, but it will take you some time, right? You need to go through a lot of cases and think about many things, right? How to think about hating algebra homomorphism. Another question: does the Rieger-Nishimura lattice have some proper homomorphic images, proper infinite homomorphic images? So does there exist a homomorphic image of this structure? Well, one is obviously identity, right? But other than identity, is there any other homomorphic image which is not itself? Okay, again, a question, very fair algebraic question. You always ask this kind of questions. Well, I don't know how to answer it immediately using algebraic methods. But here I claim that using duality, it will be just very straightforward, right? So again, let's recall what we have. So we have that duality dictionary tells us. So again, my goal is now to illustrate to you how this duality and how the duality dictionary is helpful. Homomorphic image, so it's the same as filter, is closed upset. So all I need to characterize closed upsets here. Oh, but that's much easier, right? Because what are closed upsets in this picture? So, well, I guess you could do so. So can anyone tell me what will be the closed upsets? Well, this is a closed upset, right? It's a closed set, it's an upset. This is a closed, basically picture tells us itself, right? This is a closed upset. That's a closed upset. This is a closed upset. And so now a question is there, how about infinite closed upsets? Well, one also need to figure out what kind of topology you will get there. But okay, it's also not difficult to see that what you'll get will be exactly kind of fin cofin with this being the limit point omega. So every finite and cofinite with this. Now with this, first of all, note that here I have only one infinite upset, everything minus omega, right? You could see it immediately by picture. So it's almost like proof by picture. But this one will not be, if you remove omega, this will not be closed, right? So it will be all the natural numbers, let's say, without omega. So it will be open but not closed. So the only upset which is not everything is not closed. So that's not a homomorphic image. So we just get that all the homomorphic images are of this kind. Okay.
You have 8 more minutes to finish.
Yeah, I'm almost done. Well, with this in mind, I claim that the following theorem that we proved via duality: every proper homomorphic image of the Rieger-Nishimura lattice is finite. Okay. Well, proof by duality, or I could say proof by picture, right? Because this is not so easy to see algebraically, maybe, but from dual perspective, this was straightforward. So this was just one more application of, or one application, and there are many more, of how this duality, thinking in terms of duality, could help you, because with its geometric intuition, will help you to think about, in this particular case, about structure of hating algebras and inner problems about hating algebras. So in fact, I was planning to stop here. If there's no question, I can also go through a few other examples if you like, but I'm also happy to answer some other questions. Now, for now, thank you very much. My goal was to somehow illustrate these basic ideas of the duality and their usefulness. And of course, you could see that this is only the tip of the iceberg, but at least this is the basics on which then the whole duality theory is built with all these numerous applications in this series.
Thanks a lot, Nick. Is there any question? If not, maybe we can have have a look at the examples what you wanted to show. Is there any question from the audience? Not from the offline audience, but what about the online audience?
Well, yeah, Partha.
You have?
Yeah, it's just a comment. So this is another example of an is-built duality, right?
Well, which
So-
dual do you mean duality between in the point free setting between frames and locales? Say
Yes.
It's is-built, like, I mean, is-built duality is another example of a duality. So this is also a duality, but it's of a different kind. So in that duality, you just work with complete hating algebras. Right?
Yes, you're right. I'm saying this is also, is it not a duality of between sheaves and cove pre-sheaves, open spec, where you take the Kahn extensions along the Yoneda?
I think it's of a similar kind, is duality of a similar kind, but it's not a particular, you cannot see it as an instance of that duality. I think it's a bit different. For example, in is-built duality, if you want to think in these terms, we work with complete filters, not filters, and also your category is a bit different. You don't have hating implication in the signature. In frames, you have infinite, you put infinite joins in the signature. So the objects are a bit different, but in spirit, it's somewhat similar, but I don't think you can see one as a particular instance of the other, or the other way around.
Okay, thank you.
Okay, there is one question from the audience. Just a moment.
It's not directly related to this, but like we have seen the duality in graphs, right? And right now I'm seeing duality here, and like, is there any way to connect them or somehow to see them together?
What duality do you mean in graphs?
Like we have seen dual graphs, and like there are topological aspects to it, right? And now we are looking at duality, all of these dualities here. So is there any way or view to see both of them together?
Well, here we mean duality in the categorical sense. So we have categorical sense. We have algebras and spaces, right? And that's yeah. Maybe I should go back to my very. Well, I don't know how informative it will be, but just still the very first picture. So here we say algebra and topology, connecting algebra and topology, but also after all now I can be a bit more specific what we mean. Here we have this kind of particular categories of lattices. We have categories of topological spaces or of order topological spaces. And when we say duality, we mean in a very concrete mathematical sense that there's dual equivalence between these categories. Now, in the one that you mean, also, I mean, also duality is words that you use very often in different contexts, right? So, for example, even in lattice theory, you could say change everywhere, meet with join, and then you get a dual, right? Or if you take a poset, it's dual poset is by putting it upside down, you get a dual poset. Or if you take a lattice, distributive lattice, put it upside down, you get a dual lattice, right? So the word duality could mean many things, right? So in this concrete setting, we mean, categorical duality between algebraic structures and topological setting. So I'm not sure many things could be put in many connections can be put in this mathematical framework, but I'm not particularly sure about what the graphs. And for example, when we say about lattice, take its dual lattice or change meets with joins with meets, and then it's kind of duality principles that you have. That's definitely not about dualities that we mean here. So it's always good to mean. So when we talk about duality, we mean categorical dualities of algebraic and order topological structures.
Yeah,
Yeah,
Zigzwang, you have a question, right? Yeah, there is a question from Zigzwang.
There's a question by Zigzwang.
Yeah.
Yes, so I'm wondering that so for Priestley duality and spectral duality, there's some categorical equivalence between spectral spaces and Priestley spaces. So how does this restrict to Isakia spaces and something which is a special class of spectral spaces? So I mean, what is the counterpart for the subclass of spectral spaces corresponding to Isakia spaces?
Yes, very, very good question. Again, I'm referring you to this the bitopological paper that I mentioned. So there we have a characterization of it's again so you could have a characterization. It's a bit less elegant. So at least the way we are doing it. So there are different ways to look at it. One is that a Isakia condition says that you have a Kloppen and its downset must be Kloppen, right? Now you want to translate it in terms of spectral spaces, right? So you need to say what's a Kloppen in terms of spectral spaces. That could be done, but it's a bit. So we have so it should be our definition was that I think we call it a bispectral space. So basically, it's you need to say what's a Kloppen is a closed set whose complement is also a closed set. So you need to say a closed set, and closed set is, and that needs so we call it a spectral set. So it's a set which is spectral in the subspace topology, such that the embedding is also a spectral morphism. So you already see kind of a difficult notion. And then you need to say that the bispectral, so a closed. The good thing is that the downset you can express in spectral space. In this case, it will be just closure in the spectral topology. So basically, you need to say that the closure of a bispectral space is again bispectral. This is one way to see it. So this is the analog of saying that the downset of a Kloppen set is Kloppen. There are other characterizations as well, but somewhat in the same spirit. So you use another characterization of Isakia spaces is that closure of an upset is an upset, and this also leads to an equivalent characterization in terms of spectral spaces. But as you see, so this is again a payoff between topology and order and topology, right? So you can express this particular spectral spaces, and you could also do it in terms of bitopological spaces. But I think a Isakia condition is more geometric in a sense that you could draw the spaces easier. You could immediately tell in the pictures that I showed which one is an Isakia space, which is not. And in the case of last example I gave you, again, immediately you look at duality, you look at closed upsets basically, and that gives you full characterization. In spectral sense, maybe it's still to be explored, right? Where the spectral characterization of Hating algebras could be quite useful.
And I just, as for reference,
Yes.
in the spectral space book that I've referred to, there's actually a section where this is explained for spectral spaces.
Yeah, that's another good reference. Yeah.
The condition says that if you take a patch closed set, a patch open set, a constructible set, right? So you have a spectral space, and you have this patch topology, which corresponds to the topology on the Priestley space, and then the interior of such a set is compact. That's all. It's just interior of constructible sets are compact. That's the condition. This is the Hating condition. This is the Isakia condition. So that if you look at the spectral space book, there's a section where this is done for spectral spaces.
Okay, thank you.
Yeah.
Okay.
So I think that we can take a break. I mean, break for the tea, and we will meet sharp at 4:15. I request all of the participants to be present by say
12
4:13
minutes.
at
In
least.
12 minutes.
Yeah, in 12
Yeah,
minutes.
so I promised the examples, but many of the examples you'll be also able to see on the tutorial sheet. So it's, and of course at Q&A, I will also be happy to answer any questions that you may have.
Nick, I have a request.
Yes.
Yeah, so can you say something about intuitionistic logic during the tutorial?
That
Yeah,
will be
something
great.
more.
Sure,
Yeah.
I can try. Yes.
Yeah. Okay.
I have few slides about that, so I can prefer that.
Okay. Okay.
Yeah.
Thanks.
They can make the bridges actually then.
Yeah.
Sounds good.
Because that will like close off this kind of duality properly.
Exactly. Yeah.
Okay. Sure. Yeah. I was. Yeah. There's so much you could do in 2 lectures, but I have slides of another talk. In fact, and I could take 10 minutes or so to talk about that. Yeah, definitely. 10-15 minutes at the tutorial. Yeah, sure.
Sure. Thanks.
Can I ask something? Maybe this is an outside of the.
Yes.
There are these weakenings of the Heiting condition that you can just look at pseudo-complemented.
Yes.
Lattices, and okay, so I'm fine with that. But I was recently bumping into something else, and I've kind of asked several people about this. And this is, I would like to weaken this further. I would like to have a double complementation algebra. So it means, so it's basically just, I can actually only explain this on the level of spectral spaces, and I don't know what this means on the Heiting level. So if you have the pseudo complementation, so the pseudo complemented lattices, the condition that a distributive lattice is pseudo complemented has a clear expression in the Priestley setup, and it says that. Okay, so I need to translate this now into the Priestley thing. It says that if you have maybe I can't do that. Okay, I can tell you this is in the spectral setup.
So pseudo-complemented one, that I understand well, also in the Priestley set.
Okay, good. So the question now is, the condition should be that every element has a double negation, but not necessarily a negation. And because this question comes from the fact that having a pseudo complement means it has a double complement plus a condition on the maximal points or the minimal points in your terminology of the space. And so this condition on the minimal points I understand, but I don't understand kind of this condition that having a double complement. So the question is more about if you have ever seen this on the logic side. That's what I have asked people. So is there a logic where you actually have, so you have an operator, and the operator plays the role of double negation, but you do not have necessarily pseudo negation, or so you don't have intuitionistic negation, but you have intuitionistic double negation. That's my question. Have you ever seen a logic where you have this
interesting
intuitionistic double negation, but not, this comes out of the topological setup. And
not that I have seen it, but I mean, there's one thing to say that double negation is a particular example of a nucleus.
Yes, exactly.
And so one generalization is to have a lattice with a nucleus, right?
Yes, that's exactly the question. But it's not a frame. You see, I'm asking for nuclei on distributive lattices.
Yes.
This is exactly kind of the topological symbol.
That I've seen probably. Okay, one thing to say is that even from logical perspective, I basically nuclei on a Heiting algebra. This has been studied from the point of view of logic, because these are called Lex logic. Okay,
Lex. How do you write this? Lex.
LAX. LAX.
Okay. Is this a person or what is this?
No, it's like relaxed, like
okay.
Relaxed logic.
Okay. That's interesting.
And I can give you some references. In fact, we also.
Yeah, I would be grateful. This would be.
And then basically what you are asking is a implication-free reduct of the Lex logic, right? Because
yes,
if you implication-free reduct of Lex logic, right? So, or at least a variant of that, and I think that's it makes sense to me logically. But yeah, I can send you some references.
So it's coming. So topologically, so the condition in the spectral space means something. Means that if you have an open, compact set, then you do. Then you go to the open regularization in the topology, and then you want this to be compact again. You see, they have these in I don't know in the the people are looking at these regularizations of open sets, and then they get this Boolean algebra of regular opens, right? And that's what you can also ask for open compact sets in spectral space, and that would exactly be the question. So this is the same thing. We have now talking about the same thing already in different colors. So this double negation means that if you look at the regularization, so you take closure and interior, then you get something compact. So height pseudo complemented means that the closure is a complement of a compact, and the double complementation says that the interior of the closure is compact. And this I can't find
interior of the closure is compact, because double negation is interior closure.
Exactly. It's interior closure, and so the condition is that the closure of the interior is compact again, and this is a proper weakening of pseudo complemented. And I thought there must be, as all logics that exist have already been studied, in my opinion. This might.
It's a good question. Also, what would be the Esakya condition of it? Because pseudo complementation has a very clear, because Esakya condition is downset of Kloppen is Kloppen. Pseudo complement is downset of Kloppen, upset is Kloppen.
Yes.
So it's a.
I mean, it must have a Priestley formulation. I think it's you do. Yeah. Well, I can just copy it over now, right? So I take the complement, then I take the upset, then I take the complement, takes downset, something like that. So it will have a meaning.
Yes. Yeah.
Sorry, wouldn't that be something like? Diamond box of U is Kloppen. So yes, this would be sort of. I normally think of this in terms of like diamonds and boxes because somehow it.
So yes, in the model logic setup now.
Yeah.
No, but diamond box could also mean like that diamond is just downset and box is the corresponding operator.
Exactly.
Right?
So in this setting, being sort of the diamond box, but of the Esakya spaces in a sense.
Yeah.
Right.
So basically, or you could think of closure interior of the Alexandrov topology of the pole set.
Yeah.
If you prefer not to use diamond box. Yeah, could be that, yes.
So anyway, if you send me a link to this Lax logic, I mean, I really have difficulties to find literature, and I've asked other people, and nobody has seen this before. I can't believe this hasn't been done somewhere. Some computer science people, or I don't know. Okay, thanks.
Interesting.
Yeah, so I will also come to the tutorial if people have questions about spectral space.
Yes. So Rodrigo is my student. He will also help.
So first I get a coffee. I need coffee. Okay.
What time? I forgot now. What time do we start?
I think it's rather soon. It's 3-4 minutes.
Already. Oh, I see.
Yeah. Well, you just spoke. You also can have a coffee.
Yeah, maybe I should. Do I have time to get coffee? Maybe
I will be back in 5 minutes. There are other people who are helping, right?
Yeah. Okay. Good. Is officially is it 12:45 that we start? Yes, Soren, do you remember? Oh yeah, Purbita, do we start in 2 minutes?
Yeah.
Okay.
But before that, I want to make an announcement regarding the ICLA, and then maybe we can just start.
Do I still have time to get coffee? Or yeah, maybe I can.
Why not?
I can take it afterwards. No worries. So how should we do it? So Amit had a request for me to talk a bit about intuitionistic logic. I can use slides from another talk and talk for 10 minutes about that. And,
Yeah, sure.
And then we have Rodrigo and Soren here who will be helping with the tutorial. So then maybe we could do a breakout room, or we don't want to do a break. Yeah, maybe. If we want to go over some exercises, probably it makes sense to do 2 breakout rooms.
True.
Or even 3. Yeah, maybe 2 would be enough.
Just a moment, I'm coming. On my ICLA, you could find the ICLA advertisement, not really. Where we got the ICLA wala jo indoor ka. Yeah. So, okay. Where are the participants? It's already 4:15. Please come back. Okay. So I had one small announcement regarding ICLA 2022. So actually it will going to be held. Do you remember what time? I forget. IIT Indore, but what timing? I forget.
February or March. The advertisement has been sent already.
Yeah. So anyways, maybe tomorrow I'll just show the whole scenario, what is there. But I just want to tell you that in general, we do have Indian School of Logic and Applications and Indian Conference for Logic and Applications. One is ICLA and another is ISLA. So like each alternative year we used to organize. So this time ICLA will be organized IIT Indore, and it will be not in hybrid mode or online mode, so it will be in person this time. So there are the details, and it is already, I mean, their website is already formed. So if you are interested in, please have a look at it, and also try, if you have some work in logic and you want to submit and present, please try to think about it. So that's the announcement I wanted to make. And tomorrow I'm just going to show the website from here, because actually I don't have it right now with me and we are run out of time. So Nick, you can just start with your
okay, thanks.
Tutorial session.
Either maybe one of you, could you make Rodrigo and Soren co-hosts as well? So they will be helping with the tutorial.
There is Rodrigo and Soren. So can you speak out? Then we can understand that you are audible.
Yeah, so I'm Soren. I'm going to be TAing with Rodrigo, and we are both writing our thesis with Nick in Amsterdam and studying there.
Okay.
Yeah, exactly what he said.
That's great. Okay, carry on.
All right. So yeah, well, what did I do? Okay, so upon the Amit's request, I'm gonna say a few words about intuitionistic logic and hiding algebras. Do you see my slides? So I'm
Yes.
using some slides
Yes.
from another talk. Again, it won't, maybe not too much, but at least to give some flavor. So as we know, and now that the cornerstones of classical reasoning is P or not P, the law of excluded middle. And from the constructive point of view, this has been criticized, right? So for example, if you know something, you know P if you have a proof of P. So you accept P if you have a proof of P. So for example, if P is, I don't know, say Goldbach conjectures, and P or no, we don't have a proof of P, we don't have a proof of not P. So we should not accept it from the intuitionistic point of view. So this was the criticism of Raoul of classical reasoning. For example, here's exactly the example. So back then, when I was preparing those slides, I was thinking of the same way to justify intuitionistic logic. So this led to, in the beginning of 20th century, Brouwer to reject classical reasoning, and so this is Brouwer, and to advocate for different kind of logic as for the foundation of mathematics. And Brouwer's student at the time, Hating, and that's exactly why Hating algebras are called after Hating, although Hating did not talk about algebra at all. But what Hating did, he formalized the ideas of Brouwer, constructive reasoning of Brouwer, into a formal calculus. And this calculus, you could think of it nowadays as a kind of an alternative axiomatization of Hating algebras. I showed you one axiomatization, and Hating's axiomatization was different. But eventually, if you look algebraically, the laws of intuitionistic logic are exactly, if you take an algebra that satisfies those laws, you just get Hating algebras. And if you adjust, so you could think of this axiomatization of intuitionistic logic as classical logic minus the law of excluded middle. If you take appropriate axiomatization of classical logic and drop from there the law of excluded middle, you get intuitionistic logic. So in terminal, so let's fix notation. Let's CPC with classical propositional calculus or classical propositional logic. I let IPC be intuitionistic propositional calculus. And then we know that IPC is strictly, if you think of this as all the set of all formulas valid intuitionistic or classical, we have that IPC is a proper subset of CPC. And why proper? Because the law of excluded middle belongs to CPC and does not belong to IPC. And in fact, we could think of it, CPC is IPC plus the law of excluded middle. But then the question is, how about are there other logics in between IPC and CPC? And the answer is yes, and these are called superintuitionistic logic. So formally, superintuitionistic logic is a set of formulas which extends IPC and is closed under substitution and modus ponens. So this is superintuitionistic. Now, it turns out that, that every superintuitionistic logic is also an intermediate logic. So what's an intermediate logic? Intermediate logics are those which are between IPC, which are situated between IPC and CPC. And it turns out that every superintuitionistic logic containing CPC is in fact below IPC. So intermediate, this is what I was showing that in that tutorial, but intermediate logics are exactly the consistent superintuitionistic logics. So in the propositional setting, this is almost a synonym, right? Because being an extension of IPC and be consistent, it's the same to be between IPC and CPC. So on the picture, here's intuitionistic logic, here's the classical logic, and intermediate logics are all the logics in between. What are these examples? What are intuitionistic examples of intermediate logics? KC, this is IPC plus the law, not the law excluded middle, but the weak law of excluded middle, not P or not P. This is a proper extension of intuitionistic logic and under IPC. Another classic logic, Gödel's logic, this is what Purbita asked me today. So this is exactly the models of this logic, algebraic models of this logic, are exactly the linear Hating algebras that I talked about today. So this is IPC plus this XC. Now, very quickly, well, this I know, connection with Hating algebras. Right? Every formula of the language of IPC can be translated into an equation in the theory of Hating algebras. So if phi is in this language, phi equals 1 is an equation. And the other way around, if you have an equation of Hating algebras, you can easily translate it into, well, it's equivalent to this equation, and you can translate into this formula. So this yields a one-to-one correspondence between the superintuitionistic logics and equational series of Hating algebras. And for those who are familiar with universal algebra, these are exactly varieties. So equationally defined classes are varieties of Hating algebras. So this is this celebrated theorem. Birkhoff tells us that equational series are varieties. So these are classes which are closed under subalgebras, homomorphic images, and products. So here's Garrett Birkhoff. So superintuitionistic logics corresponds to varieties of Hating algebras, and intermediate logics correspond to non-trivial varieties of Hating algebras. Non-trivial means that it's not a trivial variety, is one that consists with one algebra where one element algebra. So if we take the variety of all Hating algebras and let bool be the variety of all Boolean algebras, then we have the following, that the lattice, so this is the lattice of all superintuitionistic logics. This is the lattice of all the varieties of Hating algebras, and this theory tells you, again, duality, right? But now this, I don't mean duality in the sense of duality of categories. This is just, this lattice is isomorphic to the dual lattice of this. And why duality? Because think of it, if you add formulas to your logic becomes bigger. So classical logic is bigger. It's an extension of intuitionistic logic because it has P or not P. Whereas if you look at the class of Hating algebras, once you add a new equation to your theory, that means that you are making the class of models smaller. So hey, you have all the Hating algebras, and with P or not P, it becomes smaller. It becomes a variety of Boolean algebras. So those algebraic models that satisfy the additional equation.
Why do you say that this is not categorical?
No, you are right. Of course, it's also categorical, but yeah, good point. From high level perspective, of course, if you look at these posets as categories, that's dual equivalence of the categories. So you are absolutely right.
Right.
Somehow in my head, I don't know, Marcus, how is it for you? But for me, when I talk about duality, I always mean algebras here.
Yeah, I agree.
Topological spaces here, and you have categorical duality.
Yes, I fully agree. I don't see this as a duality in this sense. It's maybe formally a duality, but
this is an antitone-Galois connection, which is a special case of duality.
It functions.
Because Amit, let me give you another example of duality and see whether you agree with this. Take a category, any category. Reverse the arrows, take its opposite. And now this one is dual to the opposite, right? That's a duality, right?
No, that's an abstract duality. Right? There is no equivalence or isomorphism involved anywhere. So that is just formal reversion.
Yeah, but it's still formally, it's still isomorphic, dually isomorphic. But we don't believe this is not serious, right? So that's yeah. But you are absolutely right in a sense that if I think of this as a category, then this is dual isomorphism of categories. But somehow
we would call it a Galois connection. We would call it a Galois connection instead of a duality, but
well, it's a stronger version of Galois connection, right? So it's a Galois connection, but even more.
Yeah. Galois connection would be a dual adjunction. This is
So that's
dual isomorphism.
More,
right.
I think it is more about the intuition here, right? That what Nick said. I agree to this fully. That maybe you want to locate one category in algebra and the other one in topology or in geometry, and when this happens, then I think we would call it duality. Otherwise, it's maybe just rearranging the deck.
Yeah.
So there's formally maybe it's the same thing, but yeah, it's more kind of a philosophical.
Yeah, that's philosophical, and also slang, right? I mean, this is what we mean.
For a duality is simply an equivalence between C op and D, where C and D are any categories. It doesn't matter whether they are coming from algebra or topology.
Yeah, the formally is, of course, that's it. But then that's kind of the.
Anyway, thanks.
Yeah, thank you. And so to finish, so then basically this is, if you remember this triangles that I showed, you have logic, algebra, and spaces, right? So we talked a lot about duality. This is basically, I mean, this connection that I mentioned is connecting logic and algebra. So this is the Z edge. So what deduce? So consequently, we can investigate superintuitions in logics by means of the corresponding varieties of algebras. So logic y algebra, or like algebraic logic. And now the next question is how to think about, and this is where I'll stop, because then how to think about hating algebras. That's where representation and the duality comes in, right? So now logic can be translated into algebra, but algebra, to get a better grip about algebra or get extra intuition for algebra, then we do dualities, and this representation helps with that. So this is kind of connecting this triangle, and yeah. Well, the next step is to exactly maybe look at different notions on logic, like as mentioned, interpolation was one. Interpolation logic corresponds to amalgamation in algebras, and using this, say, topology or the dual structure, you get a full characterization of varieties of hating algebras with the amalgamation property, which gives you full characterization of intermediate logics with the interpolation property, which is a purely logical question, right? But so this is the game, logic, algebra, duality. This is kind of the game you play. Okay, well, this is a quick overview of upon
yeah, thanks, Nick. Thanks, Nick. For wrapping up the first order logic, categorical syntax, semantics, dualities tomorrow, this would be helpful.
Okay, very good. I can also put this on the slides if you like at the end.
Yeah, that would be helpful. I have a question now for you, like about how to manage this tutorial. So do you want to create two different groups?
Yeah, maybe we could do that. We have some tutorial sheets that we could put forward and try to.
So can you share them in the chat?
Yeah, then we can just share it here.
The tutorial, share what?
On the chat?
Can you share the problem sheet in the chat? Or was it already shared? Oh yeah, it's already.
Yeah, I can try to. Rodrigo and Soren, do you have it
in the chat? Everybody can click on the link. Yeah.
And but also we could also use it as a Q&A, right? For any further questions you have also regarding the topic. Maybe we could have two rooms. Maybe Rodrigo and Soren could be in one, and Marcus and I could be another. So it could be also Q&A for Marcus's tutorial.
Okay, I'll construct you then.
So we'll create two breakout rooms. One will contain more participants, slightly more participants, and the other one can contain fewer online participants and all the offline participants.
Okay.
Right. So we are creating that.
Yeah. So we have created two breakout rooms now. We could say that in room 1, it was the offline participants, and room 2,
one offline and one online, right? You want us to make for offline people and online people kind of things, or?
But there is also the common room where we are now, right? We can also just stay here.
So how many? There are 21 of online participants already.
Yeah, I don't know. Maybe 15 online participants could go to the online room, and then the rest and the
hybrid in the hybrid mode.
Yeah,
Okay.
yes. So I know Soren and Rodrigo. To which room will you go?
So we can go to room 2 and take the online ones, and then you can go to room 1, which is the hybrid.
Okay, sounds good.
You already broke the room, no? I can see 17 participants right now.
And you have to assign yourself to a room, because I'm not entirely sure how many should go to each. So if each participant chooses a room, it should be fine.
They are choosing by themselves or कोई नहीं है का मतलब?
They are away from computers. मुझे लग रहा है.
Is it? Oh. Oh, maybe we could help them actually, no? रूम 2 पे ज्यादा हो गया, 9 हो गया.
ये ऑफलाइन पार्टिसिपेंट्स आप लोग बात करो, कुछ बुलाया है इनको.
Oh, Srip, I think only 3 people need to join now. Okay, room 1 supposed to be offline plus online, right? नहीं है कहीं पर. Create someone.
Ask these people something. I have a question. Oh, good.
Yeah, take that.
तुम्हें room 1 में भेज देता.
किसको room 1 पे भेज रही है? Okay.
Jiguang, I'll now send you a link to that paper that I mentioned, if I manage.
Okay, thanks.
Okay, I'll take a leave now.
Yeah, this is the main room.
Okay.
Other people will slowly come or they will be forced to come.
They are still discussing on the assignments.
Yeah. So, Ziguangs, what are you doing? Are you a student or a researcher?
So I'm currently a researcher in China. So I did my master and PhD in the Netherlands.
Okay.
I did my master as the LLC.
LLC, yeah.
So I'm an academic brother of Sumit Saurabh.
Okay.
Sumit sir. Okay.
I know
Okay.
him, yeah.
Okay. Yeah.
So
I have
we have
met
the
him.
same
Yeah,
supervisor.
yeah.
Right. Okay.
So I work on correspondence theory for non-classical logics.
Right. Okay.
In the sense of Sarquist.
Mm-hmm.
Yeah, I found this this summer school via internet, and I like it a lot.
Oh, that's good to know. You can say something for tomorrow if you wish to say some for the closing ceremony.
That will be good for us. Yeah. Oh, Nick, you can be present during the. I do have that.
Oh, sorry.
So you can be present during the closing ceremony, right?
If you can.
Yes.
Yeah. Yeah. For Nick also, you have lectures or you have time, like at 4 p.m.
I think I can come to the closing. Yes.
Okay.
That's great.
Yeah. Shall we call it a day?
Okay. I'll also take leave now.
Hello, excuse me.
Yeah,
Yeah, ma'am. Actually, I got the mail that today you will discuss about tomorrow's presentation. So,
yes,
my topic was like the zones limit, its application, and there is another person with me. So,
so those who want to discuss about these topics, you can wait, but let us end the tutorial session formally.